class 19. So today we will talk about the algebraic, the Rham cohomology, and the algebraic Hodge filtration. Okay, so in the previous class, we talked about the analytic, the Rham cohomology, how to recover the Rham cohomology of a complex manifold, complex variety, just using analytic forms, differential forms. So now we will talk about how to do this in the algebraic context, okay? Just using algebraic differential forms, and we will see that we also can recover the Hodge filtration, and we can do this in such a way that we can generalize this to other contexts, not just the complex manifolds. I mean, not just for algebraic varieties defined over the field of complex numbers, but in a much generality, right? I mean, we can talk about this for schemes, but the problem is that this Hodge filtration is not well behaved in general. So now we will relate the results that we obtained in the previous class about Atiyah and Hodge and the limb, in order to explain how these results gives, in certain cases, good candidates for the Hodge filtration in this algebraic context. Okay. So, well, first of all, we'll recall what is an algebraic differential form. So let X in Cn be an affine algebraic variety. With the ideal finally generated by functions f1 up to fm. Right? Then we define the ring of regular functions as this quotient, right? And our algebraic differential forms, also called Kähler differential forms, are the following. So we define the Cx module of algebraic or Kähler differential forms as the following module. It is the module generated will denote it like this, Cxc, and it's the module freely generated by the coordinates Cx dxi, quotient by the relations given by the equations, right? Okay, so these are the algebraic differential forms over X, right? These are obviously analytic differential forms, it's infinity differential forms. It's just a subset of the differential forms that are given by regular functions, polynomial equations, polynomial functions. Okay. And well, this notation, so for every polynomial here, for every regular function, we denote this differential form. This is just formal, right? This is just formal notation, and this map is the universal derivation, right? This a C-linear derivation. So this is how you define this module, in fact, right? Linear derivation. This means that well, it satisfies the Leibniz rule, right? And it's linear. Okay. So, I don't know why. So, so now if X is any complex algebraic variety, so we have for every pair U containing in B, containing in X of affine open sets, the natural restriction maps, right? Right, and they induced natural restriction maps of these modules, right? Right, and so using these restrictions, you can define a sheaf. In fact, they determine an algebraic sheaf, and OX coherent OX module of algebraic differential forms that we denote by omega 1x. Okay. So this is the notation that I'm using. So whenever I don't put here a superindex, I'm talking about the algebraic differential forms. Okay. Okay, and this is locally free of rank. Well, it's locally free if X is smooth, right? For rank equal to the dimension of it. Okay, so we define the sheaf of algebraic K forms, just taking the exterior power of this. So the notation is like this: omega K X is the exterior power of omega 1x. And again, this is coherent and locally free if X is smooth. Okay, so an example. So consider any polynomial. Let f be a homogeneous polynomial in n variables, degree d, right? And take u to be Pn minus the zero locus of f, okay? The smooth by the per surface defined by f. Okay, so in this case, we know that this is an affine variety, right? So the differential forms, the algebraic differential forms over U are the following, right? So first of all, the ring of regular functions is exactly the ring of the algebra generated by the following rational functions: x0 to I0, xn to In divided over f to something, right? Well, over just f, where this I0 up to In is equal to d. Right, and so we can compute the algebraic forms over U, right? So we can compute this module, and it's exactly the well, I will compute it the K forms, so it will be this, so which is exactly the direct sum over, so I see U. Here I'm taking d of some element of this form, right? X to the I1 over f times x to the I k over f, right? Where these are multi-indexes such that they, when you add them up, you obtain d, right? And so in particular, every form, every k form over U must be of the following form. It's an omega tile over f to something, to m, for some omega tile. There is now a global section on Pn of the twisted sheaf of k forms on Pn on degree md, right? For some m, right? So in particular, the algebraic forms over the complement of an hypersurface are always meromorphic with pole along the hypersurface, right? So we have this equality. So if we denote J to be the inclusion, then we have that the sheaf of algebraic forms over U push it to Pn is exactly the sheaf of forms, meromorphic forms with arbitrary pole I mean, with pole of arbitrary order over X, right? Here I did name X. So here X is the zero locus. Okay. And well, this will be true in general. I mean, if you replace Pn by a smooth projective variety and X by any ample divisor, you will have this equality also, right? And this is true, and also if X is smooth projective, Y is an ample divisor, an effective divisor. And U is the complement. Then you will also have this equality. Okay, this is very elementary. Okay, so now we can recover the Rham cohomology of an algebraic variety just using the algebraic differential form. So the definition, so let X be any complex algebraic variety. Well, I think I should keep it with, well, I will say smooth complex algebraic variety. And we define the algebraic de Rham cohomology in the following way. So the notation I will use for the algebraic de Rham cohomology is this, and it is just the hypercohomology of X with its Zariski topology with coefficients in the complex of algebraic differential forms, right? Well, I didn't mention that, but in the very same way that you define the exterior differential for C-infinity differential forms, you can define it in the algebraic context, and will also give you a complex, and so you have this complex here that it's the algebraic de Rham complex on X. Okay, so the first proposition I will prove today is for X smooth algebraic variety, the algebraic de Rham cohomology is isomorphic to the de Rham cohomology. Okay. So we already did this in the analytic context, right? Here we're in a different topology. We're in the Zariski topology. This is a much smaller set of functions that we are considering, right? So what is the proof? Okay, so consider the complex of analytic differential forms, right, over X, but over the Zariski topology of X. Okay, so we have here a natural map of complexes, an inclusion of complexes, right? And we claim that this, we claim it is quasi-isomorphism. Okay, so if I prove that this is a quasi-isomorphism of complexes of shifts over the Zariski topology, I will get that the hypercohomology groups are isomorphic, right? So in consequence, we have that the algebraic de Rham cohomology, right, X over C, that is just the hypercohomology of X with coefficients in the complex of algebraic differential forms, is isomorphic to the hypercohomology over X with the Zariski topology of the complex of analytic differential forms. But this is isomorphic to the hypercohomology with respect to a covering U, where U, for U, and a fine open covering of X, right? Because since we know that the affine algebraic varieties are Stein, right? So we know that this will be a good covering for this complex with respect to this complex. And again, this will be isomorphic now to the hypercohomology group, but with respect to the analytic topology also. And this is just the, well, we already saw that this is quasi-isomorphic over the analytic topology to this shift, right? Right? We already proved that. Right? And so the only thing that we have to prove is this claim that this natural inclusion is a quasi-isomorphism in the Zariski topology. So in order to prove that, it is enough to prove that it is locally an isomorphism, right? And so it is, so in order to obtain the quasi-isomorphism, it is enough to show that the cohomology pre-shifts are isomorphic, right? So it is enough to show that for affine open sets, the cohomology group of the global sections we have here, is enough to show that these are isomorphisms for every U affine. Right? So how we will prove this? So take any U containing X affine. We already know by Hironaka's resolution of singularities that we can embed U inside some other X tilde, smooth projective, and such that X tilde minus U is some Y. It's ample normal crossing divisor X tilde. Right? And we can identify this, right? The algebraic forms over U. They are exactly the global sections of the algebraic forms over X tilde with arbitrary pole along Y. Right? Okay, and well, by Serre's Gaga, we have that this complex, we have a correspondence. So we have here for every k, the global sections of this sheaf correspond to the global sections of the analytification of this sheaf. And this is an isomorphism of complexes, right? So in particular, we have that the cohomology of global sections the cohomology of this is isomorphic to the cohomology of this other sheaf. Right. Well, but since Y is an ample divisor, we know that these sheaves are all gamma cyclic, right? This is Kodaira's vanishing, right? So by Kodaira vanishing, all this complex, right, is gamma cyclic. Right, and so the cohomology of global sections of this complex is exactly the hypercohomology, right? So this right? And so, well, but we already saw this was the Atiyah-Hodge theorem, right? So by Atiyah-Hodge, we prove that this complex is quasi-isomorphic to the complex of infinity differential forms over the complement of x tilde minus y, right? So this is exactly the hypercohomology over xn of j star of omega u n, right? And this is just the infinity, right? And this is just the cohomology of Lewis sections, and it's just the Rham cohomology. If you're right. No, but well, we already saw this also, right? I mean, this is a quasi-isomorphism with the analytic the Rham cohomology, and this is in the case where U is affine, this is Stein, so this is isomorphic to the global sections also, as we wanted, right? This is, well, it's the analytic Rham cohomology also, but okay, and this is the proof. Clear? Okay, so we have now a way to recover the Rham cohomology in the algebraic context. And furthermore, now we have, since we also have this algebraic Rham cohomology given by a hypercohomology of a complex, we can ask ourselves to what correspond the naive filtration associated to this hypercohomology. And in the case of projective varieties, it corresponds to the Hodge filtration, right? So if X is a smooth projective variety, then under this isomorphism, so the algebraic Rham cohomology is isomorphic to the Rham cohomology of X, and it sends the filtration to the Hodge filtration. Okay. Where here, this filtration here is defined to be the naive filtration, right? The image of the hypercohomology. Okay. And how is the proof? This is really very simple. So, so we already know that this isomorphism of the Rham cohomology, right? Algebraic Rham cohomology with the usual Rham cohomology, it passes through this intermediate analytic Rham cohomology, right? Right, and we already saw that the naive filtration associated to this hypercohomology group goes to the Hodge filtration here, in the case where X is a smooth projective. Okay. So the only thing is to prove that the naive filtration here, when we goes to the naive filtration here, and it's an isomorphism, right? So it is clear that the naive filtration in the algebraic side goes to the naive filtration in the analytic side, right? So what we have to show is that this is an isomorphism, that this is surjective. And since we know that this X is projective, all these groups are finite dimensional. So the only thing that we have to check is that their dimensions are the same, right? And in order to prove that, it is enough to show that the quotients of both filtrations correspond, right? That they have the same dimension. And so it is enough. Enough to show that the quotients, right? So, and also, well, we know that this the spectral sequence associated to the naive filtration in the analytic side, we know that it degenerates at E1. We proved that, right? So if we show that this spectral sequence degenerates at E1, we just need to show that at the level, at the E1, at the first page of the spectral sequence, they are isomorphic. If we prove that, we're done, right? So for us, it is enough to show that the E1 PQ of the at the algebraic side is isomorphic to the E1 PQ in the analytic side, which we know it is just HQ of xn omega p xn, right? But this is HQ of x omega p x. Right? And this is gaga. Okay? Okay, so in the smooth projective case, I mean, in the case of a smooth projective algebraic varieties, we have now this way to construct the Rham cohomology and the Hodge filtration in a very natural way, right? You just need to take the naive filtration of the hypercohomology group with coefficients in the complex of algebraic differential forms. But so we will be tempted to use this definition for in general, right? I mean, here we are not using that this variety is defined over C, right? We could do the same thing for any variety defined over any field, or in fact for any morphism of schemes, right? You can define the algebraic differential form for any morphism of schemes, and you can do exactly the same thing, right? But this is not interesting in this generality, right? In fact, even in the case of complex algebraic varieties, it's not interesting this filtration. Despite that you also recover the whole Rham cohomology, this filtration is useless when you go too far from the projective case, right? For example, so here a remark. So if X is affine, right? What happened? We know that the E1, right, E1 PQ, right, of the first page of the spectral sequence is exactly the cohomology, right, of the chief of differential forms. And we know that this is 0 for every q bigger than 0, right? And so what we are saying is that the spectral sequence obviously degenerates at E1, so it's 0. And the filtration is saying nothing, right? The quotients are exactly EPQ1, which is 0, right? So the filtration is saying nothing. I mean, in this case, FP of the algebraic de Rham cohomology, right? Of this hypercohomology is the whole thing, right? For every P. Okay, so this filtration is useless. I mean, it's saying nothing if you're not in the projective case, right? And so that's why the link reproved discover another way to reobtain the algebraic de Rham cohomology in the algebraic category, but using less differential forms than the whole algebraic differential forms. These are the forms with logarithmic poles along the divisor, right? In the affine case, right? And so, well, now I will explain why is this important. So in order to do that, I have to introduce a map. So let X be a smooth projective variety. Y be a smooth hyperplane section Okay, so here I'm not in the most general case. U be x minus y. Okay, so here I'm taking an affine variety, but this is not the most general case, right? The general case is taking y an ample normal crossing divisor, right? Here I'm just saying that this divisor has only one component that is smooth. Okay. Well, so we know that. So let C1 up to Zn be a chart such that the divisor in the chart corresponds to Z1 equal to 0. So in this case, for any form P form over X with logarithmic poles along Y, we can define, so in this open set, we define the residue around Y to be the following thing. So the residue of alpha is by definition a form beta restricted to y inter b. That will be a p minus 1 form. So I will denote it like this: J star xn. Over y and in the open set B. Right, and what is this beta? So where alpha is written locally as beta wedge d z1 over c1 plus some gamma, where with beta and gamma holomorphic forms. Right, we know that the logarithmic, the differential forms with logarithmic poles along a divisor y that is written locally like this, they are always of this form, right? And so the residue is just taking this part and restricted to the divisor. Okay, and this is the natural generalization of the residue in dimension 0, dimension 1, right? Okay, so this give us a map of a morphism of algebraic sheaves, right? So we have here the residue map that goes from, well, not analytic sheaves, right? Right here, well, J is the inclusion, right? Okay, so we have this map, and this map is in fact surjective. And what is this? Its kernel is just the space of analytic holomorphic differential forms, right? And so we have this. So this is the Poincaré residue sequence. Okay, so this is an exact sequence. Well, this is not hard to see. And so this sequence, it has a, well, since all these sheaves are coherent, it has a, so we have its algebraic counterpart, algebraic right, and it induces a long exact sequence in hypercohomology, right? So we have here. So what is this sequence? So so let's put it here. So the hypercohomology group of X with coefficients in the complex of algebraic forms is just the algebraic de Rham cohomology of X. Here we have the hypercohomology of X with coefficients in the complex of logarithmic forms with poles along Y. And here we have this residue map that will give us, again, now now it will give us the restriction of this complex to y. So we will obtain the algebraic de Rham cohomology of y, but shifted by 1, right? And it continues. Right? Okay, so what is this map? Well, before saying that, so I want to understand what is this hypercohomology group. Right, so we have this. We already know, right? We already know that in the analytic category, right, we have this quasi-isomorphism. Right, we already know that this is a quasi-isomorphism. Over the Zariski topology, right? And so this implies that the natural inclusion on the algebraic side is also quasi-isomorphism. So then this is a quasi-isomorphism. Over the analytic topology. I mean the algebraic, the Zariski topology. Right. I mean you can see this just looking at the cohomology shifts, and you will see that when you take the map between the cohomology shifts, this map when you look at the stalk, and then you take the tensor product with the module of holomorphic forms, holomorphic functions defined over the ring of regular functions, it will give you a map that is an isomorphism, right? And so it must be an isomorphism in this algebraic side, right? Okay, so we know that this is a quasi-isomorphism, and so the hypercohomology here is exactly the algebraic de Rham cohomology, right? I mean, this is the. I will put another name, I star. This right where I is the inclusion of U. So this is just the algebraic de Rham cohomology of U. Right? And so we have here that this sequence, well, in fact, it is the dual, the dual of the Leray-Thom-Gysin long exact sequence associated to the pair Ux, right? This residue map here is well, is exactly what you imagine is the analogous of that map, right? And this map is the cup with the polarization, is the cup with omega, right? So this is the dual of the intersection map, and this is the dual of the Thom map, this map that takes a cycle and enlarges it, adding this disk along each point, right? This transversal disk. And it's clear, right? It's clear that the residue must be the dual of that map. Okay, so using this this sequence, well, what the link proved, well, what he also proved. So this is something that I won't prove. So the link proved also that the naive filtration, I mean the spectral sequence associated to the naive filtration of these hypercohomology groups degenerates at E1. Okay, and so in particular, whenever we have this short exact sequence of shifts, of algebraic shifts, of coherent shifts, and we can use this sequence to produce the short exact sequence of complexes, but of truncated complexes, right? And so we can also take the long exact sequence in hypercohomology of truncated complexes, right? And so this sequence, so we know that the spectral sequence associated to the naive filtration of this complex and this complex degenerates at E1, right? And by what we saw, we know that this implies that the filtration under the Rham cohomology here comes from the hypercohomology on the truncated complex, right? By definition, the filtration is the image of the hypercohomology with coefficients in the truncated complex, right? But this image, this map, might be not injective in general. And what we saw is that the injectivity of this map is equivalent to the degeneracy of the spectral sequence at E1, right? This is a property that I mentioned. And so what we're saying is that what the link proved is that the image of the hypercohomology with coefficients in the truncated complex is injective. I mean, the map is injective in the hypercohomology here, right? And so the long exact sequence that you obtain when you truncate the complexes, this short exact sequence of complexes, is exactly the filtered long exact sequence with respect to the naive filtrations in all the hypercohomology groups, right? So this implies that the residue map respects, I don't know, the naive filtrations. Right, and so we have also this long exact sequence here of right? And so this group now, this filtration is interesting, right? I mean, it's a filtration that it's well behaved with respect to the natural residue map, right? And it fits in this long exact sequence. Now, this is a long exact sequence of filtered groups, right? And so that's why in the affine case, in this case, I mean, the affine case where the compactification is given just by adding one divisor at the infinity, we can define the algebraic Hodge filtration which is okay. So this is the good Hodge filtration in the case where U is affine and this filtration is not trivial, right? Okay, so in fact we will compute this filtration in the case where U is the complement of a hypersurface, of a smooth hypersurface in the projective space. Well, the final remark that I want to do today. So remark. So this isomorphism, right? So this isomorphism well, and well, you will see that all this machinery, all this filtration, this new definition, will be very important in order to compute the Rham cohomology of an hypersurface. I mean, this will enable us to prove Griffith's theorem in a more or less simple way, right? So, well, this isomorphism right? This is the algebraic Rham cohomology of the affine part, right? And this isomorphism is suggesting the following thing. So we know that we can compute these hypercohomology groups taking a covering, right? Taking an affine open covering of X. And when we compute this explicitly, what we will have here is a collection of algebraic forms with pole of arbitrary order along Y, right? And what we are saying is that the natural inclusion here is an isomorphism, right? But what is the image of the natural inclusion here? The image will be a sequence of forms with logarithmic poles along Y, right? and these poles are always poles of order 1, right? So this suggests that there must exist a way to pick up a representative of an element in the hypercohomology with poles of arbitrary order along y and reduce the order of the pole up to order 1. So we can obtain a representative that comes from here, right? So it suggests that there might be a way to reduce the order of the pole. Along y in hypercohomology. And in fact, this is true. There is a way. There is an operator that reduces the order of the pole explicitly. So this is the final thing that I want to do today. So this is a theorem. Well, in fact, this is a lemma due to Carlson and Griffiths. This is Carlson-Griffiths lemma, and it's straightforward. I mean, after I give you the operator to check that it reduces the order of the pole, is just doing the count. So I won't do that count. So it is the following theorem: let X contained in Pn, Pn be a smooth projective variety y given by an equation, right? Explicit equation. Be a smooth hyperplane section. Let U be Ui for I equal to 0 up to n. Be the Jacobian covering of X. This means that every Ui is the intersection of X with the set where Fi is different from 0, where Fi is the partial derivative of f with respect to xi. Okay, consider the Jacobian covering. This is an affine covering, so it is a good covering. So the operator is the following: for every L bigger or equal than 2, define the following map HL that goes from CQ U omega P X, the P forms with pole along Y of order at most L, to CQ U to the P minus 1 forms with pole of order at most L minus 1 along Y. So you define it like this: HL of omega in a multi-index J0 up to JQ is by definition 1 over 1 minus L times F over Fj0, and you take the contraction with respect to this vector field of omega J0 up to JQ. Okay, so this map this map satisfies the following thing. It is like an algebraic homotopy, but in the following complex. So then dh plus hd, that goes from this complex. So here is pq equal to k cq u omega p x ly over cq u omega p x l minus 1y to this sum. I'm sorry, this is okay, so this is the identity. Right? So so here, this is the quotient of the complex, the simple complex associated to the double complex given by the check resolution of this complex of sheaves, right? And so what we're saying is that whenever you take some omega that it's here, right, in this direct sum, right? So whenever you take an element of the hypercohomology associated to the complex of algebraic forms with pole of arbitrary order along y, there will exist some L such that it is inside here, right? Obviously. And then when you apply the operator 1, well, and you take a guy here such that d of omega is 0, then this operator, then in the hypercohomology, omega will be exactly the same as 1 minus dh omega in hypercohomology, right? So this will be also representative of the hypercohomology class of omega, but the pole order will be reduced by 1, right? Because when you look at this in this quotient, right, you will get that this is the identity. This is 1 in this quotient. So 1 minus this part is exactly this applied to omega, which is 0, right? So when you apply this map to omega and you look at it in this quotient, it is 0. This implies that it is here in this other complex. So you're saying that the pole order along y of this representative is at most L minus 1 along y. And so you can apply this inductively and obtain a representative that will have at every level a pole of order at most 1, but the differential of these guys, since the d of this representative is 0, when you apply d, the differential d, to any of these representative, it must be equal to the check differential of the other representatives that also have order of pole at most 1. So the d of any of these guy will also have pole of order at most 1, and so it will be a logarithmic form, right? And so this is the way that you can prove this isomorphism constructively, right? This is an explicit way to construct this isomorphism, okay? And we will use this in the next class to to prove Griffiths theorem. Okay, questions?